All right. So today we're gonna get into start to talking about reactions. Well, the basics of reactions, and we're gonna talk about uh, the types of reactions, and that's where we're gonna start. Types of reactions, and then we're gonna talk about bond making and bond breaking processes. And eventually we'll get into like some thermodynamics, talking about enthalpy and activation energy and delta G and uh, uh, like how to determine whether a reaction is exothermic or endothermic. So we're going to get into that as well. This is actually a very good section. And a lot of what we learned about acids and bases is going to apply, especially with the arrows. And the only difference is here is instead of acids and bases, Bronsted acids and bases, now we're going to be talking about Lewis acids and Lewis bases, which conceptually are different, but also the same, right? So it's the same principles. Electron sources and electron sinks, nucleophiles, electrophiles, all of that follows the same. Those concepts fall in line with acids and bases, except we're not looking at proton transfer. We're looking at other types of bond forming reactions. All right. So we're going to first start out talking about the types of reactions. And there are 4 basic types that we're going to discuss. And I have a little exercise for us to do to warm up, looking at the different types of reactions. And today is the 17th. I said 16. That's because I made this yesterday. All right. So we're going to look at substitution, elimination, addition, and rearrangement. Those are the 4 major types of reactions: substitution, elimination, addition, and rearrangement. All right. And so we're gonna rather than me just verbally telling you what each one is, we're gonna look at some examples, and based on those examples, we're gonna determine the definition for each one. All right. What I will tell you is that if it's elimination and addition are the reverse of each other. Right. So a lot of times the addition reaction will be the forward reaction, and elimination will be the reverse reaction, going back to the addition start material. But we're going to talk about it. All right. And then substitution is going to involve a leaving group. And it's going to get replaced by what we call a nucleophile. I'm going to abbreviate nucleophile for now. All right, so addition and elimination are inverses, and then rearrangement is kind of the movement of a like it can be an atom, or it can be electrons, or it can be both. Let me not say movement. Let me say migration. Migration of atoms or electrons. And I'm going to say intramolecular. And I know that's bad syllabification, but you got it, you'll get it. So migration of atoms or electrons intramolecularly, meaning within a molecule, right? So let's go to these examples here, and I have a bunch of examples that I made just for this purpose. So we can see what's happening in each example, and we're actually going to talk about how it happens and define what process or what transformation happens. All right. And so having said that, we're also going to reintroduce curved arrow notations. Right. And we said that a curved arrow that's double-headed means that I'm moving 2 electrons at a time. And a curved arrow that's single-headed means that I'm moving 1 electron at a time. And this particular process is going to be polar. And then this process is going to be radical. Right. And let me go ahead and introduce the bond making and bond breaking before I get to these examples, because we can apply it when we're doing the examples. So when you're breaking or making bonds, you do so using curved arrow notation, right? That's how we're going to write we already have looked at mechanisms, but this is how we're going to write mechanisms using curved arrow notation. So when we think about a mechanism for a reaction, right? It is an illustration. Right? It's an illustration of the steps to convert starting materials into products. And we show it by using curved arrow notations.
What does SM stand for?
Starting materials.
Thank you.
Yeah, I'll write it out. I apologize for that. And PDTS is products. Right, so the star material is always on the left side of the arrow, and then the products, I'll write that out too. So the next time you see that abbreviation, you'll know what it means. And RXN is a abbreviation for reaction. Right. So when we talk about a mechanism, it's a way to illustrate the steps that happen from as the star materials are reacting together to become products, right? And we show it by using curved arrow notation. There are going to be 2 types of mechanisms. We just talked about that, a polar mechanism. I mean, that means that if it's polar, everything is going to be 2 electrons moving at a time, right? So if I have a, let me just do a generic reaction here. So if I have this plus, I'm gonna write this out. Plus that. All right, and I want to attack carbon with the electrons on sulfur. And there's a reason why it's attacking carbon and not bromine. And again, everything goes back to what we learned in the first couple of weeks. There's a dipole between these two. Carbon is partially negative. Bromine is, I'm sorry, carbon is partially positive. Bromine is partially negative. And so when sulfur attacks, it's going to attack at that partially positive site, right? Because of that dipole. Because sulfur is, again, if you look at what it's doing, the arrow from sulfur to carbon means that sulfur is donating a pair of electrons. So it's not going to donate electrons to an atom that's already electron rich. So sulfur in this case is what we call a nucleophile. A lover of nuclei, right? It's looking for, and you know the nucleus of every atom is positive, right? Because it's just protons and neutrons. So it's looking for a positive charge or a partial positive. Now I say seeking, I don't want you to think I'm conferring some type of like human properties onto atoms or molecules, but it helps to think of it that way because it makes it make sense, right? So it's seeking positive charge. It can be partial positive or full positive, doesn't matter. But we call that a nucleophile. You'll see that abbreviated like this. That's Nu with a pair of electrons over the U, right? And nucleophiles and polar mechanisms, nucleophiles react with what we call electrophiles. Right? And just like a phile on the end comes from the Greek word philos, for love, one of the Greek words for love. So that is a lover of electrons, right? Lover of electrons. So in this particular case, if it loves electrons, the atom in the electrophile that's going to receive the pair of electrons has to have at least a partial positive on it, right? So we call that atom, which would be right here in this case, in the electrophile. The whole thing is electrophile, but there's a site that's the most reactive, and that's the carbon because it's partially positive. We call this the electrophilic site. Right, because that's where the electrons are going. Because it's partially positive. All right, so when sulfur attacks, I'm also going to lose bromine. Also going to lose bromine. So this is a type of substitution because sulfur is going to replace, the nucleophile is going to replace the leaving group, which is bromine, right? So on the other side of my arrow, this is my starting materials. I put the arrows in to show how the starting materials interact with each other to get to the product. So on the other side of the arrow, I have this. I'm gonna write this out like that. Plus Br minus. Right? Questions about that part, about anything we just did. So you got a nucleophile, you got an electrophile, they get together, they share electrons, and they make new bonds. You also broke a bond. So that's the part that I want to talk about now. The bond making, excuse me, and the bond breaking. Go ahead, Sanaya.
So when I look at the curved arrows, I think of like when we were trying to I guess break like an acid or base. This is
Mhm.
different. We're looking for, I guess, the partial positive, not for
Yeah.
like hydrogen breaking.
Yeah, so you're not really, in this case, you're not looking for a proton to attack, but you're looking for a polarized bond, right? And normally, like for the scope of this class, a lot of our electrophiles are going to be carbon based. Not all of them, because some other atoms can be electrophiles too. But for the scope of the class, it's mostly going to be carbon. But it's the same. If you notice, the flow of electrons is very similar, right? The nucleophile is a electron donor, just like the base is an electron donor, was an electron donor in the acid base chemistry. And then the electrophile is an electron pair acceptor, kind of like the acid or the proton of the acid was an electron pair acceptor, right? So it's very similar, and the electron flow is almost identical, right? Because I still have to break that bond between carbon and bromine in order for carbon to accept that pair of electrons. So if you know how to push electrons between acids and bases, it's the same flow of electrons between nucleophiles and electrophiles. You just have to find the electrophilic site. And once you do that, then you'll know where to put the electrons. And if you notice the arrows, again, this is vitally important. I started at a pair of electrons on sulfur. I ended at the atom where I'm trying to make the bond, right? That's really important. I didn't put them all off into space somewhere, or pointing, to some other atom, or pointing to hydrogen, or pointing to bromine. I put my arrow where I want those electrons to end, which is on carbon. So that's where I'm trying to make my new bond. So here is the new bond that I made. I hope that answered your question too, Sanaya.
It did.
So I made a new bond, and I also broke a bond, right? So now let's talk about, for polar reactions, bond making, and then bond breaking. All right. So for bond making in a polar reaction, we call it heterogenic. Genic in the sense of formation. For bond breaking, we call it hetero. And I'm going to explain this using a generic example. Lytic. Right? All you biology majors, you know something about lysis, right? Lytic means to cut, or to lyse means to cut. So it's heterolytic. So when I break a bond in a polar fashion, it's heterolytic. When I make a bond in a polar fashion, it's heterogenic. So if I have an atom, this is what hetero means. So it means the two species that are reacting are different. So if I have an atom like this, A, and I'm reacting it with B, and B is positive, both electrons are coming from A. Right? That's heterogenic. When I make a bond between A and B. So that's heterogenic. So polar processes, bond making is what we call heterogenic, where one atom supplies both electrons. And you can see up here, the sulfur supply both electrons to make that new bond. Let me actually change the color of that bond too. Right? So sulfur supply both electrons to carbon to make that new bond. And then by the same token, if I break a bond, let me just show it with the same example. And both electrons go with one atom. You can see that here. If I have a double-headed arrow in between the bond, means when I break it, both electrons in that bond are leaving with one atom. Right? So this is going back to A minus plus B plus. Right? So this is what we call heterolytic. Right? So both electrons are going to leave with one atom. Now, all this stuff is esoteric right now, right? Just, you know, in the ether. But when you think about, go back and think about, we talked about functional groups and what they do and how they make certain molecules, you know, behave. That's when all of this stuff comes into place. You know, bond making and bond breaking is going to be different on something that's electron rich versus something that's electron poor, right? Something that's electron poor is going to be looking for electrons. Something that's electron rich is going to be looking to give away electrons. And different functional groups make molecules either electron rich or electron poor. So that's how that all ties together. So we have another term up here, because your nucleophile is electron rich. So we call it a source. And then your electrophile, which is trying to heterogenically get a pair of electrons and make a bond with the nucleophile, we call that a sink, right? And in a polar mechanism, electrons are always going to flow from nucleophile to electrophile, or from source to sink. Just like in an acid-base reaction, electrons always flow from the base to the proton of the acid, right? It's the same ideas, you're just applying it to a different set of substrates. All right. So polar mechanisms are heterogenic, and heterolytic, bond making and bond breaking. And they involve a nucleophile and an electrophile, or a source and a sink. And when we write out those mechanisms, we use curved arrows to show how the start materials get converted into the product, which is on the other side over here. All right. Any questions about that, or about anything that we talked about so far? Let me zoom out. All right. So now let's talk about radical mechanisms, and then we're going to jump into these other examples because we got time. So we're going to talk about radical mechanisms, and in order to do that, I'm going to do another example like we just did. And I'll use radical substitution Substitution is the easiest to illustrate, so I'll just use another substitution reaction. So with a radical mechanism, everything is one electron. Right, so I'm going to use another substitution reaction. So I'm going to do, I'll use bromine again. Right, so you'll see right away that a radical is a species with a single unpaired electron. And you've heard this terminology before, free radicals. That's why antioxidants are a big thing, right? They were, especially when everything, on the market, food and nutrition wise was, it's rich in antioxidants. It has a lot of antioxidants. And the reason why those compounds were thought to be important is because they scavenge free radicals in the body, right? Because radicals are highly reactive and they can do a lot of damage to molecules, especially molecules that can accept an electron. So that's why in the late 90s, the early 2000s, everything was all about antioxidants and free radicals. So free radicals have a single unpaired electron. They're highly reactive. And yeah, when I say highly reactive, I mean highly reactive, right? So if I have a radical here, and with the radical mechanism, there's no nucleophile or electrophile, right? Because everything is either what we call homolytic or homogenic. So if I have a radical here and I have another radical here, like that, the way that I illustrate the mechanism is to show those two radicals coming together to make a new bond. So I'm going to write that out over here. So it's Br right, and there's the bond between them. Right, so there's no nucleophile, no electrophile in this particular case because both atoms have a single unpaired electron. You can see that right here. So they're going to react together, right? So in this particular case, we made a bond, and the bond breaking processes for radicals, we call it homogenic. If a bond is being made, and if a bond is being broken, we call it homolytic. Right, so an example of the bond making process, let me show you that. So if I have let's say if I have a chlorine radical, and I'm going to react that with let's just do another carbon radical here, right? When I combine these two like so, notice both atoms have one electron to donate, right? So when I make that bond between them, right? This is homo, meaning same, homogenic. It means that both atoms have one electron to donate, and they just share that electron by overlapping orbitals. That's not a minus sign, right? And if I cleave the carbon chlorine bond, so I have something like this, and I break the bond between them. Notice how my arrows are. They're single-sided or single-headed, like a fish hook. That's indicative of a radical reaction, right? You can't use a double-headed arrow to illustrate a radical mechanism, because you're not moving two electrons at a time, you're only moving one. Right, so I broke this bond here. Right, and this is an example of what we call homolytic cleavage. So homogenic, homolytic are the terms that we use for radical reactions. And then heterolytic and heterogenic are terms that we use for polar reactions. All right, any questions about that? So we're going to go back to what our initial discussion was, which was the types of reactions. But I wanted to show you this so that when we look at the types of reactions, we'll know, okay, this had to be a radical reaction. This had to be a polar reaction. We're going to combine this information all together when we're looking at the different types of reactions. All right. So let's go to the next page, unless there's a question about what we just talked about. Right. So on this page, it says classify each transformation as a substitution, elimination, addition, or a rearrangement. And we're going to add a layer to that by saying whether or not it's polar or radical. All right. So the first reaction you can see, all right, I have a diol on this side, and then I have a ketone on the other side. The first hint that a reaction that happened is an elimination is the formation of a pi bond. So anytime you see a pi bond formed in the product, you can see that CO pi bond. That's going to indicate that there was an elimination that took place. Right? And what I want to do now is kind of show you how this, a proposed mechanism for this this reaction. Add a page. Right, so you'll see what I mean by when I say an elimination. So elimination we're going to lose I'm gonna put group in quotes because it's not really a group. It can be an atom, it can be a functional group of atoms, but you're going to lose a group. So it's the loss of a group resulting in the formation of a pi bond. So loss of a group that's going to result in pi bond formation. Right, so I want to show you the elimination step. So we're going to start, I'm going to just redraw this. right? So if we had to propose a mechanism for something like this, and this is, you know, don't worry about not understanding this right now, right this second. What I want to show you is the elimination part, or the loss of a group. So elimination, again, loss of a group or functional group resulting in pi bond formation. So the first thing I'm going to do is a proton transfer. Don't worry about that part. We've seen that before. And it's internal, meaning that the proton is not coming from another source. So we call that intramolecular. Right? Meaning something happened within the same molecule, intramolecular proton transfer. All right. So having done that, I'm going to get to an intermediate that looks like this. And then O, H. Now that's positive. Does everybody agree with that? If I pull off that hydrogen on the oxygen on the right, that's going to leave it as a negative charge, or with a negative charge. And then it's going to also, that proton has been added to the oxygen on the left. So now that oxygen now has two hydrogens attached to it, and it gives it a formal charge of +1. Anybody not see that?
Can you explain it one more time?
Yeah, sure. So the arrow from this oxygen to hydrogen means that is going to form a bond with hydrogen. Is that right? So I can see that right here. And then this arrow from hydrogen back to oxygen means that I'm going to give that pair of electrons to oxygen. Because it's just a proton transfer. It's an acid-base reaction, right? The oxygen on the left side is my base. It's attacking the proton on the oxygen on the right side. So it's a proton transfer. Now for the elimination part, what do I have to do an elimination? I have to lose a group. Is that right? So the group that I'm going to lose is going to be that water molecule. And I'm going to force it out. So I'm going to put this pair of electrons here, and I'm going to give these to oxygen like that. So that's going to give me this. And now I've made a pi bond right here with oxygen plus, right? So this is the elimination step. Right, so that's the elimination part right there. Loss of a group. You see that? I lost water. And then I formed a pi bond.
I have a question.
Go ahead.
So for the proton transfer, does it happen simultaneously, or is it kind of like like the lone pairs donated and then, the hydrogen donates the electrons to the oxygen to break that bond? Does that happen simultaneously?
Yeah, that's all at the same time. So
Okay.
as the oxygen is donating that pair of electrons to hydrogen, the other OH bond is breaking?
Okay.
Yeah, great question. All right, so this is an example of elimination. You lose a group, and when you lose that group, you form a pi bond. And if you notice, every bond breaking and bond making process in here is either heterogenic or lytic, right? So the loss of water is heterolytic. The formation of the pi bond, that's heterogenic. The loss of proton on the other side, that's heterolytic. The formation of the OH bond, that's heterogenic. So this also would be classified as a polar reaction. But the type of reaction is an elimination. And the way you can tell if an elimination happens is when you make a pi bond in the product. And you can see going from the diol to the ketone, you most definitely get a pi bond. All right, questions about that? We only got like 2 minutes left. I think we might be able to squeeze in one more of these.
I have a question.
Go ahead.
Can you go back to the problem and
Mhm.
repeat which ones were heterogenic and all that?
Oh, sure. Can I abbreviate that? Because I could just, so heterogenic, we're gonna say HG. And then heterolytic, we'll say HL. Y'all like abbreviations, right? Kind of. Somewhat.
So that worked.
Yeah, so right here, the OH bond formation, this would be heterogenic, right? And then the OH bond breaking right here, see how both electrons are going back to oxygen? That'd be heterolytic. Same over here. You see how the oxygen is leaving with that pair of electrons. So that's carbon oxygen bond is breaking. This would be heterolytic. And then this carbon oxygen pi bond right here is forming. So we'll call that heterogenic. So everything, because this is a polar reaction, everything in that reaction is going to be either heterolytic or heterogenic. Did that answer your question?
Yeah, so the breaking of a bond is
Lytic.
lytic.
Mm-hmm.
Okay.
So think about cutting, right? To lyse is to cut. So if I break a bond, that means I'm cutting the bond between the two atoms. So that's lytic. If I make a bond, think about creation, like Genesis. So that's heterogenic. All right. All right, any other questions? I'm not gonna try to squeeze in another example. We're gonna pick this right back up on Monday. We're gonna go through the other reaction types, and then we're gonna start looking at some nucleophiles and electrophiles, and we're gonna look at thermodynamics, calculating enthalpy, determining whether it's exothermic or endothermic, writing energy diagrams and things like that. So we're gonna just stop here. I'm gonna give y'all a little break. The exam will be posted. I think it'll be posted at 11 today. You'll have all the way to Sunday at 11:59 to finish it. You can start it, stop it, open notes, whatever. And then I'll send you videos on Sunday for Monday. But I sent you a good bit on Wednesday or Thursday for today. So make sure you watch those, read the sections in the textbook that are in the readings list in module 2A. And we're gonna just keep trucking. Believe it or not, we're almost halfway through this class, which is crazy because we've covered, this is the 4th module that we're in right now. And there are only 8. So we're just gonna keep trucking. Keep trucking.
I have a question.
Go ahead.
So we can turn the homework in, I guess, for the module 2 and begin like